Tensile and compressive loads are among the most common types of loading encountered in structural components. Consider a column supporting a heavy load, which is therefore subjected to compressive stress. Tensile loads, on the other hand, occur in ropes, chains, or bolts. To ensure the functional safety of components subjected to tension or compression, it is essential to know the relevant material properties. The tensile test has proven to be a central part of material testing for determining these limit values. The tensile test not only provides values for tensile loading. Empirical investigations also allow conclusions regarding strength in compression, shear, and torsion. For this reason, we will first examine the tensile test in detail. More extensive information is available in the linked video. In the tensile test, the load-bearing capacity of a material under increasing tensile load is determined. The specimen is stretched until fracture, while the required force is recorded as a function of elongation. The figure shows a typical curve obtained during a tensile test. The force elongation curve obtained from the tensile test does not directly provide stress limit values, as force alone does not describe the intensity of loading. Therefore, the tensile stress sigma is calculated as the quotient of force and cross-sectional area. For example, a stress of 250 newtons per square millimeter means that each square millimeter of cross-section is subjected to a force of 250 newtons. Stress is thus a relative quantity describing force in relation to cross-sectional area. Likewise, elongation is not given as an absolute value in millimeters, but relative to the initial length. This parameter is called strain epsilon and is dimensionless. For clarity, strain is often expressed as a percentage. For example, a strain of 0.01 means that the material elongates by 0.01 meters per meter of original length, corresponding to 1%. The originally geometry-dependent force elongation diagram is thus converted into a largely geometry-independent and therefore material-dependent stress-strain diagram. The qualitative shape of the curve remains the same, as only the initial cross-sectional area and initial length are used to scale it. Material behavior under tensile loading can be divided into three main regions in the stress-strain diagram. In the first section, stress increases linearly with strain. This is the linear elastic region. In this region, the specimen returns to its original shape upon unloading. In the subsequent uniform plastic deformation region, the specimen experiences permanent deformation after unloading. In this plastic region, the cross-section decreases uniformly along the entire length. At the point of maximum stress, the specimen begins to neck locally and continues to deform only at that location until it eventually fractures. This region is called the necking region. The stress-strain diagram allows determination of two particularly important parameters in strength of materials. The first is the limiting stress up to which a material can be loaded without permanent deformation. This elastic limit is referred to as the yield strength Re and marks the end of linear elastic deformation. The second important parameter is the maximum stress a material can sustain before necking and subsequent fracture. This is the tensile strength Rm. For materials without a distinct yield point, the stress-strain curve transitions smoothly from the elastic to the plastic region. In this case, the 0.2% offset yield strength is used instead of the yield point. Graphically, this is obtained by drawing a line parallel to the linear elastic region at 0.2% strain. The intersection of this line with the stress-strain curve defines the 0.2% offset yield strength. At this point, the material already has a permanent deformation of 0.2%. In general, components must not undergo permanent deformation during operation. Therefore, a material should ideally be loaded only up to its yield strength under tension. If this limit is exceeded, the material deforms plastically and becomes unusable. This results in a fundamental criterion for the dimensioning of a component subjected to static tensile load. The tensile stress acting in the component must always be lower than the yield strength of the material used. Consider the following example. A cylindrical bar made of S235 structural steel has a diameter of 10 mm and is to be subjected to a constant force of 20 kN. The question is whether this bar meets the strength requirements and remains elastically loaded. To check this, we first determine the internal stress under the load of 20 kN. Using the formula for the area of a circle pi/4 times the diameter squared, the cross-sectional area is 78.54 square millimeters. The tensile stress inside the bar, calculated as the quotient of the acting force and the cross-sectional area, is thus 255 newtons per square millimeter. We now compare this stress with the yield strength. The steel designation S235 indicates a yield strength of 235 newtons per square millimeter. The comparison shows that the stress present in the bar is greater than the yield strength. The elastic limit is therefore exceeded, and the bar undergoes permanent deformation. The 10 mm diameter is therefore insufficient to prevent permanent deformation. The cross-sectional area must be chosen such that the resulting stress remains below or, at most, equal to the yield strength. In practice, components are never designed exactly up to the yield strength, but always with a substantial safety margin. This is necessary because operational conditions may cause unpredictable temporary increases in stress. Moreover, the yield strength is determined under standardized test conditions that may not reflect real-world applications, for example differences in specimen geometry, surface quality, temperature, or loading rate. Therefore, a safety margin must always be maintained. Depending on the application, especially if failure could endanger human life, the allowable stress may be significantly lower than the yield strength. For the considered steel bar, an allowable stress of 94 newtons per square millimeter may be specified and must not be exceeded. In this case, the yield strength is about 2.5 times higher than the allowable stress, providing sufficient safety margin. The safety factor, defined as the ratio of yield strength to allowable stress, is symbolized by the Greek letter nu. In practice, the safety factor is usually determined based on empirical values. The maximum permissible stress used for dimensioning is then calculated from the safety factor and the yield strength. What diameter must the steel bar now have, so that the specified maximum permissible stress of 94 newtons per square millimeter is not exceeded? To calculate this, we rearrange the stress formula to solve for the cross-sectional area to be determined. If we insert the maximum permissible stress, we obtain the minimum required cross-sectional area for a given force. After inserting the numerical values, a cross-sectional area of 213 square millimeters is obtained, which is the minimum required. The corresponding diameter for a circular cross-section is obtained using the formula for calculating the area of a circle. After rearranging the formula to solve for the required diameter and inserting the numerical values, a minimum required bar diameter of 16.5 millimeters is obtained. Note that the values for cross-sectional area and diameter, regardless of the exact decimal places, are always rounded up so that the maximum permissible stress is not exceeded. In this way, the calculated diameter of 16.5 millimeters ensures that the maximum permissible stress of 94 newtons per square millimeter is not exceeded. In summary, the most important formulas for the dimensioning of a statically tension-loaded component are presented again. These include the definition of stress as the quotient of the acting force and the existing cross-sectional area, the calculation of the maximum permissible stress based on the yield strength and the given safety factor, and the determination of the minimum required cross-sectional area from the acting force and the maximum permissible stress. Note that components do not always have to be designed against permanent deformation, where the yield strength serves as the governing strength parameter. In some cases, components can also be designed against fracture, for example with shear pins which are intended to break at a defined overload. In such cases, the tensile strength serves as the governing value. Also, for very brittle materials, such as cast iron, where a yield point is very difficult to measure, the tensile strength is usually used as the strength limit value instead. Even if the preceding dimensioning based on strength criteria ensures that the yield strength is not exceeded under a tensile load, it must still be noted that the component elastically stretches during this process. This can potentially lead to problems. Let's consider the example of a pressure vessel sealed with a lid. The lid is fastened to the vessel with bolts. The force exerted on the lid by the prevailing pressure is transferred to the bolts as a tensile load. Even if the bolts can withstand the pressure in the vessel without permanent deformation, they will still deform elastically. If the bolts stretch too much in the process, the clamping force between the lid and the vessel decreases, and sealing may no longer be guaranteed. In this case, therefore, not only strength limits but also deformation limits must be adhered to. In addition to the dimensioning of components according to the required strength criteria in the form of maximum permissible stresses, components must therefore generally also be dimensioned according to the required deformation limits in the form of maximum permissible strains. Thus, it is important to know the relationship between an existing stress and the resulting strain in order to check whether strains might be too large. In the elastic range, where components are fundamentally only permitted to be loaded, the stress-strain diagram shows a linear relationship. Mathematically, This relationship is described by a straight line through the origin. In this case, y denotes the stress sigma, and x the strain epsilon. The slope of this straight line is a characteristic material parameter and is referred to as the modulus of elasticity, or Young's modulus, symbolized by the capital letter E. The Young's modulus establishes the relationship between the applied stress and the resulting strain. It must be noted that this relationship only applies within the elastic range, in which components are only permitted to be loaded. A modulus of elasticity for aluminum of 70 kilonewtons per square millimeter means, illustratively, that a force of 70 kilonewtons is required per square millimeter of cross-sectional area to theoretically stretch the material to twice its original length. For cast iron, Young's modulus is typically around 120 kilonewtons per square millimeter and is nearly twice that of aluminum. Steel has a Young's modulus around 3 times that of aluminum. Thus, steel requires 3 times the stress to produce the same elastic strain. Young's modulus can therefore be interpreted as a measure of stiffness. The term modulus of elasticity is somewhat poorly chosen, as it does not express the elasticity of a material, but the opposite, its stiffness. The larger the Young's modulus, the less the material deforms under a given stress. All important formulas for dimensioning based on strength and deformation criteria are summarized once again. Consider the following example. 2 plates are spaced 100 millimeters apart. A hex bolt of alloyed steel with a metric ISO thread of property class 9.8 clamps the plates together. The upper plate is subjected to a load of 10 kilonewtons. Under this load, the spacing between the plates may increase by no more than 0.1 millimeters. The question is, which metric thread must the bolt have to ensure a safety factor of 2 against permanent deformation? In this case, 2 criteria must be satisfied. Permanent deformation must be prevented with appropriate safety, and the specified maximum elongation must not be exceeded. Dimensioning therefore follows both strength and deformation criteria. First, we determine the maximum allowable stress that prevents permanent deformation. For this, we need the bolt strength properties, which are given in the property class 9.8, also called strength class. This designation contains both tensile strength and yield strength. For example, consider a bolt of property class 4.8. The tensile strength is given by multiplying the first number, 4, by 100, resulting in 400 newtons per square millimeter. The yield strength is obtained by multiplying this value by the number after the decimal, 0.8, giving 320 newtons per square millimeter. For the 9.8 bolt in our example, the tensile strength is 9 times 100, which equals 900 newtons per square millimeter. The yield strength is then 900 times 0.8, which results in 720 newtons per square millimeter. Using the yield strength and the specified safety factor of 2, we obtain a maximum allowable stress of 360 newtons per square millimeter. This ensures prevention of permanent deformation, but does not yet account for excessive elastic elongation. We therefore calculate the stress at which the elongation of the bolt reaches the maximum value of 0.1 millimeter. To do this, we first determine the strain as the quotient of the maximum change in length, delta L max, and the original length, L0. We obtain in this case a maximum strain of 0.001, which must not be exceeded. Expressed as a percentage, this corresponds to a maximum strain of 0.1%. Using the Young's modulus for steel of 210,000 newtons per square millimeter, we can now determine the corresponding stress that leads to this strain and must not be exceeded, as otherwise the distance between the 2 plates would increase by more than 0.1 millimeter. Note that in the formula, the strain is not inserted as a percentage, but as the value of the quotient of elongation and original length. In this way, we obtain a maximum stress of 210 newtons per square millimeter, which must not be exceeded. We therefore see that in this case, it is not the exceeding of the permissible strength limit of 360 newtons per square millimeter that is critical, but the exceeding of the deformation limit of a maximum of 210 newtons per square millimeter. For dimensioning, the lower of the 2 stress values must therefore be used as the basis. If we insert the maximum permissible stress of 210 newtons per square millimeter with a given force of 10,000 newtons, we obtain a minimum required cross-sectional area of 47.7 square millimeters. With this information, we can now determine the required bolt diameter. However, caution is advised when determining the appropriate bolt size. One must not now determine the bolt diameter using the just calculated cross-sectional area and the formula for a circular area, as in the example of the previously considered bar. The critical factor for a bolt is not the diameter of the bolt shank, but the load-bearing area in the cross-section of the thread. To examine this, let us consider the bolt in cross-section if we cut it through at the level of the thread. We can see that the nominal diameter of the bolt, that is the diameter measured at the crest of the thread, includes the thread profile. However, this thread profile does not carry the load in the bolt. The hatched load-bearing cross-section is smaller than the nominal cross-section because of the cut thread. This hatched area, over which the stress in the bolt is ultimately distributed, is referred to as the thread stress area. The stress area does not need to be calculated manually, as standardized tables provide values for each nominal thread size. In this case, we need a bolt with a thread stress area of at least 47.7 square millimeters. Looking at the relevant tables for metric threads, the first size exceeding this value is 58 square millimeters, corresponding to thread size M10 with a nominal diameter of 10 millimeters. Thus, M10 is the appropriate bolt size that meets both strength and deformation requirements. Finally, we consider the dimensioning of components subjected to compression. In the formula for the maximum allowable stress, a yield strength exists not only for tensile loading but also for compressive loading. Dimensioning under compression is analogous to tensile loading. For compressive loading, the relevant limit is the compressive yield strength, which is determined in a compression test and defines the stress above which plastic deformation occurs. While steels have nearly identical tensile and compressive yield strengths, cast iron typically withstands much higher compressive stresses than tensile stresses. Consequently, compressive yield strengths are significantly higher than tensile yield strengths.